Okay, good afternoon. So I want to finish up something that I left off last time. So last time we did this Laughlin argument where we had a cylinder and we threaded the magnetic flux through the cylinder, and this system looked just like a thallus charge pump. When we threaded a quantum of magnetic flux through the cylinder, then an integer number of electrons could be pumped across the sample, and that integer then told us that the Hall conductivity had to be that integer multiple of E squared over H. Okay, and so what I want to show you now is that so when I discussed the thallus pump, I related that integer, the amount of charge that gets pumped, to the churn number. Okay, and so what I would like to do is to relate that churn number computed for the thallus pump to the churn number characterizing the two-dimensional band structure of the state that is wrapped on this cylinder. Okay, and so I want to do that construction. So, okay, so in order to do that, so I imagine now that I have some Hamiltonian, which is a two-dimensional Hamiltonian. So I have some two-dimensional, let me call it insulating state. Let's imagine that we have a band structure. Okay, so I'm not doing Landau levels. I just have a two-dimensional band structure. And so I have a Hamiltonian, which is a function of kx and ky now. Okay, but I've wrapped it on the cylinder, and so what that means is that the values that ky can have are going to be quantized, because of the finite circumference of the circle. And so in particular, what we're going to have is that ky, now the magnetic flux that's going through the cylinder changes the values that ky can have. So what the values that ky can have, it's going to be basically 1 over the radius of the cylinder times some integer plus phi divided by phi naught. Okay, and so what you can see from this is that when I advance the flux by 1 flux quantum, then what I've done is I've taken, so this m is an integer, what I've taken is I've taken all of these integer quantized values of ky and I've shifted them over by 1. Okay, so and so of course I've come back to myself, all I've done is rearrange which states I call which. And so so now what we have is we have a system where if I view as a one-dimensional system as a function of kx, then I have lots of different one-dimensional subbands, which are all the different values, all the different values of m. Okay, and so viewed as a one-dimensional system, what I then want to do is do the calculation that I did last time to compute the charge that gets pumped. Because what I showed you last time is that the charge that gets pumped can be computed as the churn number associated with this pump. Okay? And is there a question? No. Okay. Where on which picture? Where on the cylinder? Well, I have a two-dimensional system. Oh, which direction is y? Oh, good. Yeah, sorry. That's good. So this is x, and then y is like this. So y is compactified on a circle, so that the ky is then going to have discrete values. Okay, but the magnetic flux changes the boundary conditions, sort of changes the phase that you pick up when you go around, and so that shifts ky by this amount. Is that, am I clear? Okay, good. Okay, so now the only thing that's a little bit more complicated now is we have many subbands. Okay, and those subbands are indexed by M. Okay, and so if I treat it as a thallus pump, then my charge that gets pumped, it's going to be a sum over all of the subbands of E over 2 pi times the churn number, which I told you is the integral over kx, and the integral over the parameter, which in this case is the flux, of the Berry curvature, F, which is now a function of Kx, and it's a function of the flux, but it depends on the flux. The flux and Ky are sort of go together. Okay, so it also, I'll put it as flux, like this. Okay, but if I think about this, so let me draw a picture of Kx and Ky. So here's my two-dimensional Brillouin zone. So this is Kx and Ky. And so what I'm doing is I am, so when I put it on the finite cylinder, I'm giving myself sort of discrete values that Ky can have. Okay, and so what happens when I turn on the flux? I can say, let's suppose this is the line, Ky M at flux 0. Then this would be the same one, Ky M at flux phi naught. Okay, so basically, these states, when I turn up the flux by a flux quantum, they move up to the next one. Okay, and so what I can do then is, so when I'm doing an integral, and I'm summing over all of these lines, and so when I do the integral, then what I'm effectively doing is I'm integrating. When I integrate phi to phi naught, I'm effectively integrating K over this region here. Okay, and so hopefully what you can see is that after I do the sum, then I basically added up all of these, and so what I end up with then is E over 2 pi times an integral over Kx and Ky, now over the whole Brillouin zone of now the Berry curvature, which now I can interpret as a function of Kx and Ky. Okay, and so this is the churn number characterizing a 2D gapped band structure. Okay, and so if you follow the logic that we went through, what we've just showed is that sigma xy of this is equal to this. Okay, and so now I'm talking about a two-dimensional system the whole time. Okay, now so now this result that the Hall conductance is the churn number. So this is a famous result by Thales, Komodo, Nightingale, and Denise. So this is TKNN, and it's 1982. Okay, and so now, so actually, this is not the calculation that they did. Okay, so the calculation that they did was actually to calculate sigma xy. Okay, and so sigma xy is something that you can compute using linear response theory, using the Kubo formula. And so what they showed is that when you compute sigma xy by the Kubo formula, you get the same formula as the formula for the Chern number. Okay, and so that's an alternative way of getting that result without taking this detour into one dimension.
So can you just connect this to the previous lectures? In the previous lecture, you talked about Thales pump as well.
Yes.
But without introducing.
Well, so there I was talking about a generic one-dimensional system. Okay, where I had a one-dimensional band structure characterized by kx and a parameter which I called time. Okay, and then what I had was I showed that the charge that gets pumped is basically I only had one band. Okay, and then this was my parameter.
So literally, you could phi, the function of time, you could change variables and put that into
Yeah, this literally is Thales's pump formula. That's what I'm trying to show you, is that since I showed you the Thales pump formula, I've done all of the work necessary to show that the Hall conductivity is the two-dimensional Chern number. Okay, so that's what I, and somehow I felt that was simpler than doing the linear response calculation. Okay.
So this is how Thales discovered it. I mean, he did both, except he did it in the other way around.
Yeah. Yes.
In the second equation, aren't you still summing over ends?
No, because if I take a single term in this sum, then that's integrating over just this little region here. Because a single term, I'm integrating over phi, and that takes a single ky from here to here. Okay, but then if I add them all up, then I get the whole thing. Okay. Okay. So what I'd like to do now is see how this plays out in a simple model system. I always like to do these things in a two-band model if I can. And if I can't do it in a two-band model, then maybe I'll do it in a four-band model. But we can do it in a two-band model with this. And so I want to introduce a model system. Which is graphene. Now, of course, we heard about graphene this morning, and Pablo showed us that graphene is not just a model system, it's actually a system. But I'm going to treat it as a model system, okay? So let me just remind you some basics. So you have a honeycomb lattice. So let me draw a couple of pieces of the honeycomb lattice. Yeah, that's probably enough. I don't know. So, okay. So the point is that I have an A. So there are two sublattices, an A sublattice and a B sublattice. Maybe I should call it. Well, yeah. And I have a Hamiltonian. On nearest neighbors of just nearest neighbors on the honeycomb lattice. Okay, so okay, so you see the honeycomb now. So and I can write this in terms of a 2x2 matrix in the same way that I did for the Sushri-Verheger model. And so again, I can write this in Fourier transform. I can write it as a sum on k of ck, let me call it little a b times sum hab of k, where hab is going to be a 2x2 matrix. It only involves hopping from between the A and the B sublattice. And we have to specify, so if we want to write this down, we have to specify that there's sort of three different bond vectors. and let me call them R1, R2, and R3. Okay, and there's a little bit of geometry to work out how long they are and things like that, but that's not really going to concern us. Okay, so you're basically going to have on the off diagonal sum on j of e to the I k dot rj, and a sum on I of e to the I with minus I k dot rj. Okay, so this is the Hamiltonian, and I can write this if I like as d dot sigma, the same way I did before. Okay, and what we then conclude is that dx is going to be equal to minus t sum on, I guess this is sum on j, sorry. Okay, so this is pretty basic. Okay, now one thing that it's useful to do is to think about symmetry a little bit. Again, I thought about symmetry in the Symmetry model. Let's think about the symmetry here. Let's think about the symmetries that this has. So one obvious symmetry, there's no sigma z term, again, so it has the same chiral symmetry that the Symmetry model had. So it has chiral okay. Of course, that's not a real symmetry of graphene. Okay. Graphene could actually have second neighbor hopping terms, which would violate this chiral symmetry. Okay. It also has inversion symmetry. So under inversion, so there's inversion, say about the, you can invert about either the center of the hexagon or the center of a bond, and that interchanges the sublattices. And so inversion tells us that h of minus k is equal to sigma x h of k sigma x. And it also has time reversal symmetry, which at this point, let's just imagine that we're not talking about spin for now. And so time reversal symmetry just takes the complex conjugate. Okay? And so that says that h of minus k is equal to h of k star. Okay, and so these together give constraints on what the form that this D can have. And so in particular, I want to think about PT symmetry. And under PT, that says that h of k is equal to sigma x h star of k sigma x. And if you think about that, that requires that dz of k is equal to 0. Okay? So actually, we don't need the chiral symmetry in order to forbid the dz term, provided we have p and t. Okay? So provided we have P and T, though, we have this situation where this D vector is can only live on the equator of the circle. Okay, the Z component has to be equal to 0. And so what that allows, so now it's a function, D is a function of Kx and Ky, and so this allows point defects. In momentum space, around which D wraps by 2 pi. Okay? And that's precisely the Dirac points. So maybe I'm going to have to put this up and then go to the next one. Okay, so of course what happens in graphene, so if I draw the Bro1 zone, it's a hexagon. And as Pablo showed us this morning, there are these two special, so there's the K points, and then there's the minus K, which is also K prime, which are these. Okay, and of course, these 3 points are actually the same point because they're related by a reciprocal lattice vector. Okay, and so at these points, then we have the famous Dirac cone. Okay, and this Dirac cone I can think of as being kind of like a vortex where D winds wraps around the circle when I go around it. Okay, and it goes around one way around K, the other way around K prime. Okay, so at the Dirac points, we have D at plus or minus K equal 0. Okay, and so what it's useful to do then is to expand near these Dirac points. Okay, and so if I ask then, it's a exercise to go through if you haven't gone through this before, to actually show that if I put K equals the corner of the Bro1 zone in here, that these are both equal to 0. Okay, and so that's algebra that if you've studied graphene, you've already done, and if you want to study graphene, you need to do it. So.
Could you please explain again how you came to
I came to the conclusion because symmetry guarantees that this D vector lies in the plane. And if you have a vector that lies in the plane and it's non-zero, then in principle you can walk around a circle and have that wrap by 2 pi. If it wraps by 2 pi, then there has to be a singularity in the origin, because as I shrink down, then I can't shrink that continuously to nothing. So there has to be a point where D actually goes to 0. That's the only way out, is to have D go to. If D didn't go to 0, then any circle you'd be able to contract down to nothing. Okay, and so these Dirac points are protected in that sense.
Does it do all the line defect?
I don't think there's any reason you'd have a line defect. That would not be protected. Okay. I mean, you could, but a small perturbation would get rid of it. Okay. All right. So if I look near these Dirac points, so I'm going to expand for small q. So I'm going to do the same kind of low energy, long wavelength theory that I did for graphene, that I did for the Sushri-Verheugen model yesterday. And so if you do that, then what you find, if you expand, it can only involve sigma x and sigma y, and so it's like that. Okay, and I think you can check from this that it actually respects these symmetries, those symmetries, and actually it was important that this minus, this plus and minus sign be there in order to respect those symmetries correctly. Okay, and so good. Now I want to make a point here, a couple points. So first of all. So the full symmetry that graphene has, it also has a threefold rotational symmetry. that sort of fixes the Dirac point to be at this corner here. Okay. If you were to relax that rotational symmetry, but keep P and T, then these Dirac points, they can't go away because they're a winding number. You know, they're sort of topological, but they could move. Okay, so they'd still stay there. Okay, in a sense, you could say that these Dirac points are protected by the pi Berry phase that an electron has going around. If you have P and T, the only choices for the Berry phase is 0 and pi. And so if it's pi, you can't get rid of it. Okay. Okay. Now, okay, so look, Dirac points, they're interesting. And Pablo has shown us that there are lots of interesting things that you can do with them. But as a model system, I like to think of Dirac points as being interesting because that you can get rid of them in interesting ways. And so what I want to think about is what can you do by lowering symmetries to get rid of the Dirac points, to open up an energy gap. Okay? And so in general, by lowering the symmetry, I might be able to add some mass, some sigma z term, okay? And like this, okay? And maybe it's the same at k and minus k, or maybe not. So I could have two different mass terms, okay? And so if I do this, of course, then my energy is going to have a gap. Okay, and so what I'd like to think about is what is the structure of the different kinds of gapped states that I can have. And what I want to remember, so what I'd like to, in particular, think about is I'd like to think about the Chern number. Okay, and ask myself whether I can construct a gapped state that has a non-zero Chern number. Okay, and so how do we think about the Chern number? Well, in this two-level system, we have a very simple way of thinking about the Chern number that I taught you yesterday. So remember, the Chern number n is so yesterday I called it the wrapping number for this vector d. And Nick told me that that's actually not the correct technical term. So the correct term is the degree of d of kx and ky. Okay, on S2. Okay, so basically it's counting the number of times that d, which sweeps out a area on the sphere, how many times does that wrap around? Okay, and so this is this very simple pictorial way of thinking about the Chern number. And so I want to think about that for different ways of introducing gaps into graphing. So one way I can do it is I can break inversion, but keep T. And so this is, for example, what happens in boron nitride. So Pablo showed us, told us about boron nitride this morning. That's where on the two sublattices of the graphene lattice you put different atoms. Okay, and so that introduces a sigma z term into the Hamiltonian, and so I can have my Hamiltonian is going to be some m sigma z, and m plus is equal to m minus. Okay, so I'm basically just putting a plus potential on the A sublattice and a minus potential on the B sublattice. And so if I do that, so let's think about what the Chern number is going to be if I do that. So again, I have my Brillouin zone. Okay, with my points, K and K prime. Actually, let me do this one. Okay, and that is getting mapped by D onto the surface of a sphere with the equator. And so what's going to happen now is most of the interior here, if I imagine that this staggered potential is very small, so most of the place it's not going to have a very big effect. So all, throughout here, this is all going to go basically to the equator. Okay, but if I look precisely at the K point, then the D that I had before is equal to 0, so it's going to be dominated by this term, and so it's going to go up to the North Pole. And maybe do a different color here. No, what a sublattice piece does, so a potential that only gives me a potential on the A sublattice just gives me a constant here, and something that has a potential on the B sublattice gives me a constant here, and so a staggered potential is going to be like sigma Z. Yeah. Well, you could have perturbations that change things here. Those would involve changing the bonds. So, for instance, if you were to strain the graphene to make maybe this bond different from this bond, or this bond, then you would add terms on the off diagonal. But the effect of those terms is not going to be to open a gap, it's going to be to move the Dirac points around. Because those terms wouldn't keep the D in the plane. Okay. Okay. So the point is that I still got the wrong color. Shit. Which color did I use? This one? There we go. Okay, so the point is that K goes to the North Pole, and so you can sort of think that it's in this general region here, it's sweeping out up here like that. Okay, but K prime also has the same sign. So if I look near K prime, it's also going to the North Pole, and so it's also going to sweep up like this. And so this is sort of like this doesn't wrap around at all, right? It wraps around on the top and then it goes back again. Okay, so the degree of this map is 0, and so and as we should have already known from the start, boron nitride is a trivial insulator. Okay. All right. There's another choice, though, okay, which is to break T, and we can keep P. Okay? And so this is an insight that was really first noticed by Duncan Haldane in, I think, 87, something like that. Okay? And so here now, so how do you do this? How do you break T? So one way you can do it is you can take your graphene lattice and you can have a magnetic field where the magnetic field, say, is 0 on the average, but maybe it's fluctuating between being positive and negative. Okay, and so since the magnetic flux is 0 on the average, you don't have Landau levels. Okay, you still have Bloch's theorem, you still have a band structure which is a function of kx and ky. Okay, so there are no Landau levels, but you have managed to break time reversal symmetry. And in a tight binding model, you would know about this flux if you include second neighbor hopping terms. Okay, because they would know that you enclose some non-zero flux. Okay, so that's the model that Haldane wrote down, and but so we can sort of think about what's happening here. So if we inversion symmetry, which I can do with this magnetic field, then what we know is that from the second thing up here, we know that the mass at plus k has to be equal to minus the mass at minus k. Okay, and there's no reason, once we've broken time reversal symmetry, that this mass has to be equal to 0. Okay, and in fact, it's not 0 if you do this tight binding model. And so what happens in this case now, if I think about, mapping my my Brillouin zone to the sphere, again, most of the interior gets mapped to the equator. The K point still gets mapped to the North Pole, and around there. The K prime point gets mapped to the South Pole. Okay, and so now you can immediately see that this wraps around the sphere once. Okay, and so this gives us a quantum Hall state without Landau levels.
Does this model involve doubling the size of the unit itself?
No. No, it doesn't. If you look, every unit cell looks the same as every other unit cell. Well, no, but think in terms of the magnetic flux.
The magnetic flux is the actual pumping out.
No, so the physical problem of a physical magnetic field, that obviously has the full translation symmetry. And it is possible to choose a gauge that also has the full translation symmetry. Because all I have to do is have a second neighbor term and choose the phases on these second neighbor hopping terms. And that's the model. And those are the same in every unit cell. Good. Okay. Okay.
But in this case, do you need to deal with that translation?
No, you don't, because the average flux is 0. So let me just digress for a minute about this. So at first sight, the Landau level problem seems very different from band theory, right? Because the Landau level problem, you have this problem that the translations in the x and y direction don't commute with each other. The momentum in the x and y direction don't commute with each other. Okay, but if I have a lattice, so let's imagine that I'm doing the Landau level problem. Okay. And I just draw an artificial lattice that has a unit cell that encloses a quantum of magnetic flux. So I choose my unit cell to be exactly the right size that there's a quantum of magnetic flux in the lattice. Okay? So it's true that my continuous translations do not commute with each other, but the lattice translations do commute with each other. Okay, and so if I do a translation by this direction and a translation by this direction, that's the same as doing a translation by this direction and a translation by this direction, if it encloses a quantum of magnetic flux. And so what that allows is even for the original Landau level problem, you could think of it as a band structure on this lattice. With Bloch's theorem and a Hamiltonian as a function of kx and ky. And of course, if you do it for the, without any actual periodic potential, then you just get flat bands, and those are the Landau levels. Okay. Now you could also contemplate putting on a periodic potential, And this is actually the context in which Thales originally introduced this idea of the TKNN invariant, because what he was interested in doing is looking at the quantum Hall effect in a periodic potential which could be commensurate with the magnetic flux. Okay, and so there's an interest, that leads to this interesting Hofstetler problem, and that was really where the original idea of thinking about the Chern number and things like that came from. Yeah.
I missed the point about, you think of the continuum problem, not the level problem, but introducing this kind of a phantom lattice.
Yeah, yeah. So I only try to characterize the crystal momentum, not the total linear momentum. And so the crystal momentum is, well, yeah.
How do you see from that perspective that there's a flat band?
Well, because we know the answer.
Okay.
We can look in the book, back of the book. Nick did the calculation this morning or yesterday.
And indeed, there's one state.
Exactly. That's right.
Okay, that is the unit.
Yeah. Okay. Okay. So some more mileage we can get out of this simple model picture. We can get the edge states.
Just to be clear, the TKNN invariant is in fact the Chern number.
Yes, absolutely. And if that was not clear, then
In this particular model, it's 1.
yes, that's right.
And it's actually the same as the degree that you're talking about.
Right. Okay. Okay. So of course there's a simple classical picture for the edge states. If I think in terms of cyclotron motion, the electrons are going around in circles, but if there's a wall, then the electrons can bounce along the wall. Okay, and that motion is a special kind of motion because it only goes in one direction, which suggests that there should be propagating one-way states on the boundary. And so that's something that is interesting to see if I think about a boundary where I have a boundary between these two phases. Okay, and so what's happening on the boundary between these is, well, one of the two masses at either k or k prime is changing sign. Okay, and so I want to imagine now a boundary between somewhere where I have a quantum Hall state where the two masses are opposite to each other. Okay, so this is a n equals 1 quantum Hall state, and one where the two have the same mass, and so this is going to be n equals 0 trivial insulator. Okay, and so in both cases I'm going to have a band structure that has a gap. So this is energy as a function of k. In both cases I have a gap, but to get from one to the other, what has happened is the conduction band and the valence band have sort of inverted. Okay, so there's a band inversion. Okay, and so I can think of this, if I think about the mass m plus, so I can keep m minus fixed. All the action is at the k point, and so what I'm doing is I'm just changing. I'm going from say a mass which is negative to a mass which is positive. Okay, so it looks just like the Jakiv-Rebbe problem that I solved for you yesterday or the day before. I can't remember when I did. Okay, so we can do this. So So what we have now, so if I still have that. So I have my Hamiltonian. I can write this down now. I still have, so let's call this the y direction. So this is y and this is x. Okay? And so I still have momentum in the y direction, but now I have to treat x in real space. So I'm going to have minus I sigma x d by dx plus ky sigma y. And then now I have the mass term, which is m plus of x sigma z. Okay, and so this, if I fix ky, this looks just like the Jakiv-Rebbe problem that we solved. Okay, and it has the same solution. Okay, and in particular, I'll have a, so solving the problem in the x direction, I'll have a zero mode. So it's going to be a function of ky, and it's going to be a plane wave in the y direction. But then it's going to be this same exponential piece times. So actually, there is a slight difference in the Jakiv-Rebbe problem, which is that the sigma operators have different letters on them. But that doesn't matter. Okay, you can, instead of x, y, and z, I could have. It's just a change of basis. So in particular, though, so these are going to be the zero modes are going to be eigenstates of the product of sigma x and sigma z, which is sigma y. Okay, so on one of the sides it's going to be a let me write it as sigma y plus, the plus one eigenstate of sigma y. Okay, and in particular though, since that zero mode is the plus one eigenstate of sigma y, its energy is going to be V plus Vf times Ky. Oops.
Before you didn't have sigma y in your Hamiltonian.
That's right. That's right. But the zero modes are eigenstates of sigma y, so that just pushes the zero mode, changes the, so now applying this Hamiltonian, this part is going to give 0 and this part is trivial. It just gives, Vf Ky like that. Yes. Oh, yeah, good. So what I mean is that, so if I look at just the, let's look at just the states at q equals 0, right at the, at q equals 0, and ask what do those look like as I change this, as I vary m plus from being positive to negative. Okay, and so what's going to happen is at the point, m plus has to go through 0, and at the point where it's 0, the conduction band and the valence band are exactly touching each other. Okay, and so these lines I can think of are following the states as they go through, and so it's as if the conduction band, if I look just at the conduction band, it's as if I follow them through and they're sort of switching places. So if I follow the states at exactly q equals 0, then the conduction band and the valence band invert. So that's what I mean by the inversion. It sort of turns upside down. The conduction band turns into the valence band. The valence band turns into the conduction band. Of course, away from away from Q equals 0, then there are terms that couple them together, so you always have an avoided crossing. So it's not like when in the inverted state there are no crossings, right? But you're basically going from something that looks like this to something that looks like this to something that looks like this, and if I follow this state, it goes to this one.
Exactly the plot.
Yeah. Yeah. Oh, this? Well, this is the mass as a function of x. Yeah. Yeah. Okay.
So what about n larger than 1? Is that the sign, is it plus or minus?
What n larger?
N larger than 1. So now the Chern number is 1.
Yeah, the Chern number is 1. Yeah.
What about 2 or 3?
Well, you could do that. The simple way I could do that is I could just put 2 Haldane models on top of each other. Then I could have n equals 2.
Yeah, I understand. I'm saying now this looks sort of like putting plus or minus on
Well, no, it's not Z. So it's certainly true in this 2-band model. With this band inversion, I can only change the Chern number by 1. So if I have this transition where 2 bands switch places, then that describes a transition where the Chern number changes by 1. Okay, so a transition where the Chern number changes by 2 would be something different, and I think generically it would probably split into 2 single transits, 2 single ones. Go to what? I don't think in this model you get nu equals 2. I don't think. Well, yeah, you'd have to do something else. I mean, maybe if you include further neighbor hoppings and do things, you might be able to get nu equals 2 in that case. But in the single, the Haldane model, which only includes second neighbor hopping, I don't think that nu equals 2 is anywhere in the phase diagram.
Because the number of Dirac
Okay. All right.
And that's an argument of the one direct. Well, with the other, you have KMT prime.
Right. Well, so in order to go from here to here, what I need to do is change the sign of one of them. I mean, I could do either one, and I could change the sign of m minus instead of changing the sign of m plus. That would be just as good. Okay.
Nothing happens to the other side.
Right. Yeah. I just keep the gap stays finite. Yeah. Okay. So. Right. Just so the upshot is if I look at the energy as a function of kx, then there's the bulk states which form a continuum. But in addition, localized on the boundary of this, we have this 1D chiral Dirac fermion. Pardon me?
How do you know the chirality is this way or not this way?
Yeah. So that depends on whether the normalizable zero mode is an eigenstate of sigma y with eigenvalue +1 or -1. And that depends on which the sign of the kink is. Okay, whether you're going from minus to plus or plus to minus. And so for that, you can obviously see that the two edges if you have two edges of your quantum Hall state, then one edge is going to be going one way and the other one's going to be going the other way. Okay. Okay. So these chiral Dirac fermions are very magical and special things, right? Because they're only going in one direction. So if you're an electron, then you have no choice but to go forward. Okay? And so that means that if there's disorder, disorder doesn't get in your way because you just keep going forward. So these states are impossible to localize, and and one has perfect transmission in them. You put an electron in over here, with 100% certainty it's going to come out the other side. And so it's really this fact that you have this perfect transmission that's at the root of how it could possibly be that in the integer quantum Hall effect, in an imperfect sample, you can measure a perfect Hall conductivity, at least to 1 part in a billion. Okay, so these are very special things. So another point that I want to make is that these chiral Dirac fermions, it's impossible to have a chiral mode like this by itself purely in one dimension. Okay, and so there's a theorem okay. So I think this goes back to Nielsen and Ninomiya, is that right? So and applied to this simple one-dimensional case, the way that one can say it is what goes up must come down. So if you have a one-dimensional band, then I should be able to draw the band structure in a Brillouin zone. And so if I have a band that goes up, well, it has to go back down in order to match onto itself. Okay? And so that says that chiral modes have to occur in compensating pairs. Okay? Now, so you can ask the question, how did we get around that? And the way the quantum Hall effect gets around it is, now of course you always have, if I think of my quantum Hall system as a one-dimensional system, it has a top edge and a bottom edge. I have my right and left movers, which have to be there by this doubling theorem. The magic of the quantum Hall effect is that it spatially separates the right and left moving modes, okay, so that they can't talk to each other. Okay, and so there's no theorem that forbids having a chiral mode which is in a different place from its partner. Okay.
This chiral mode, that after it touches the box, it then continued or it simply merged with the box?
That depends on the details. So I mean, of course, actually, no, it has to. It has to merge because eventually I get around to the other side of the Brillouin zone. So if it didn't merge, then it would have to come around over on this side, and then it would keep going. So I think it generally merges. But where it merges, that's a detail that depends on the specifics of the problem. Yeah.
Because this is in 2 dimensions, and we have weak localization in 2 dimensions. So if I consider a limit where...
Well, we have a gap, right? We have an energy gap. The two-dimensional bulk is like an insulator.
So it's not...
There's no two-dimensional weak localization. Now you could ask yourself, we have a one-dimensional edge, and you might think that, well, one-dimension localization is even worse. Okay, but this gets around that because there's nowhere to backscatter to. Okay, and so that changes it and evades the theorem that says that every state is localized in one dimension. Okay. All right. Okay, so I am going to get to topological insulators eventually. But I thought what I would do is just say a couple of more words about things that one can understand without imposing more symmetries. Okay? And so I want to talk about some generalizations of these ideas. And the simplest generalization, you could say, well, could I imagine, so the quantum Hall effect is something that exists in 2 dimensions, a 2-dimensional electron gas. Could there be anything in 3 dimensions? Okay? And in fact, you can. It's kind of trivial. You can imagine building a 3-dimensional system up by just making a stack of 2-dimensional systems. Okay? And so this is something that was studied by Halperin back, I think it was in the early 80s, or something like that, maybe 83. I don't remember when it was, but in any case, so certainly if you just have layers that are completely independent of each other, then what you know is that if I have my 3-dimensional system, it's going to have lots of edge states that go around the sides. Okay, and so if I think about a 3-dimensional band structure, how could I characterize this? And so if I look at the 3-dimensional Brillouin zone, then clearly if I have this stack of independent layers, then everything's going to be independent of kz. And so if I evaluate on a plane a 2-dimensional plane, I can have a Chern number, which is the integral dkx dky of f. Okay, and so a Chern number is defined. And in fact, even if I start coupling these layers together, so I can't think of them independently anymore, I really have a 3-dimensional band structure, I could evaluate this Chern number on a plane. And one thing I'm guaranteed, since the Chern number is a topological invariant, if I vary kz and look at this, the parallel planes at different heights, then the Chern number has to be the same. Okay, and so this Chern number characterizes this 3-dimensional band structure. So now there's a Chern number in the z direction. There's also going to be a Chern number in the x direction and a Chern number in the y direction. Okay, and so the 3 together they define a triad of 3 integer topological invariants, and they can be associated with a reciprocal lattice vector. G, which is like if I have a lattice constant of a, 2 pi over a times nx, ny, and z. Okay, and this gives a quantized Hall conductivity. Let me write it as sigma ij is equal to epsilon I j k g k. Okay, times e squared over h. Okay, and notice this is a 3-dimensional conductivity. It involves the lattice constant h or a, which is basically giving me the Hall conductivity per layer. Okay, so this is a 3-dimensional. It's kind of a trivial 3-dimensional generalization of this quantum Hall effect.
Is it obvious that you just do that?
That I can do what?
Like you can just add up. Okay, you understand it for one plane, you understand it for 3 orthogonal planes.
Well, maybe it's not immediately obvious, but it's true. So you can ask yourself. Now, of course, I can take any plane in the Brillouin zone and define and integrate F and define a Chern number. Okay. The question is how many of those numbers are independent? Okay, and it turns out that you only need to know 3 of them. And if you know those 3, then you can evaluate any other. It's just like in order to, there are lots of reciprocal lattice vectors, but in order to get any one, I only need to know 3 of them, and then I can add them up to get it. So in fact, the invariant really is a reciprocal lattice vector, and the way I can interpret that reciprocal lattice vector is I can interpret it as the Miller indices that characterize these lattice planes.
But also, I mean, you argued for this by starting with a 2D quantum halls and making a weak state.
Yeah.
But you're saying you kind of approached this limit from
Just because that's something where we already know the answer.
Stacks, 3 different.
Yeah. Those are 3 cases where we already know the answer. But, you could say, what if I did a different stack in the 1, 1, 0 direction or something like that? And I'm telling you that the Chern number I define with that is not independent of the 1, 0, 0 Chern number and the 0 and the 0, 1, 0 Chern number.
No, but what I'm worried about is that as you increase the hopping between the planes, would you not have a transition where you can't think of it as a 2D quantum hall?
Well, you could have transitions to different phases. Sure. But what I'm saying is that any one of these 3D quantum Hall states can be adiabatically continued to something like this in some direction. In the direction which is lattice planes, indexed by these Miller indices.
Aren't you eventually looking at 3D sample where the hoppings, let's say, all the same?
Not necessarily.
Suppose you look at
if they're all certainly if I have rotational symmetry, like cubic symmetry, then this is impossible, right? Because G is a vector, so it has to be invariant under the symmetries of your crystal. Yeah.
Choose your 2D plane in the 3D bundle to calculate the Chern number for.
How can I choose it? Well, I can choose all of them. I could evaluate this one. The thing is that once I choose a direction normal to the plane, then it doesn't matter which height it's at, because since the Chern number is topological, it can't change it characterizes the entire family.
Unless there's a wild point.
But I'm assuming there's a gap. Yeah.
Because the definition involves crystal structure and the lattice spacing, shouldn't this kind of be more sensitive to disorder than the usual quantum hall?
Yeah, I think it probably is. I mean, notice that the Hall conductivity is not an integer in units of fundamental constants. There's a number A that it depends on that has units. So it's not quantized in the same sense that the two-dimensional quantum Hall effect is quantized. Okay, but the Chern number is well defined, and the Chern number guarantees these edge states on the surface. You still can't get rid of those. Okay, so I want to do another generalization. So we did 2 dimensions, we did 3 dimensions. So why stop there?
The direction of a magnetic field determines the G that you're looking at? I'm sorry, I'm confused.
Well, I don't even necessarily need a magnetic field. Haldane did,
Okay, you're saying that's Chern numbers are allowed.
Yeah.
But okay.
But certainly so this physics actually, I think, at least on some level, shows up in these Beshgard salt materials is Paul Chaikin experiments, where but this is in a magnetic field, where they see this three-dimensional kind of quantum Hall physics. So certainly it could be in a magnetic field, but in principle it doesn't need to be. Now, I don't know of any examples. It would be nice to come up with a magnetic material that breaks time reversal symmetry that is in one of these quantum Hall states. I don't know of any that exist.
Right. But when you say, suppose I have a model that realizes that model is characterized by 3 integers. So it has 3 given integers.
Any three-dimensional crystal has 3 integers. Usually they're all equal to 0. With a gap, exactly, yeah.
For a particular model that realizes this kind of a 3D quantum Hall effect, it'll just have 3, not any set, but 3 integers, and that defines it.
Well, yeah.
Characterize the model.
Yeah.
There's only one G vector.
There's only one G vector.
One
That's right. That's right. They're just 3 numbers that you need to know. And if
It's
you
not
know...
like it's not like any plane or any direction.
That's right. No, that's what I'm saying, is that yeah. So...
You could obtain this result in a more topological way. You could apply a bit more technology and ask yourself how to characterize the band structure in the fluid zone.
Yeah.
And you would find that, it's described by second Chern product.
No, I disagree with that.
No, I didn't mean second. I mean second cohomology.
Okay.
8 up 2.
You mean this is counting the number of holes in the Brillouin zone?
Exactly this.
Yeah.
If you evaluate it on a 2-dimensional slice, you get some integer.
Yeah.
Which depends on which slice.
Yeah.
And it's basically your integer.
Right. That's right.
That's the intrinsic construction.
Yeah. Yeah. Okay. So I want to move on from 3 dimensions to 4 dimensions. Oh, I'm sorry. Question. If I had some kind of what? Instanton for the Berry phase. What do you mean? You mean by instanton as a function of kz? Is that what you mean? That's what you mean? So then that's a Weil point. Yeah. Yeah. Okay. Okay. So if you go up to 4 dimensions, so there's a sense in which this 3-dimensional quantum Hall effect isn't really anything different than the 2-dimensional one. It's just a stacked version of the 2-dimensional one. If you go to 4 dimensions, you get something which actually is new. And so this is this was work first written down by Zhang and Hu. And so here, in order to do this, I'm going to be a little bit more sketchy and generalize this notion of the Berry connection and Berry curvature to situations where you have more than just one band, and where the Berry connection now becomes a matrix. Okay, and so this is sort of a generalization. If I have more than one band, then I can define a non-abelian, let me call it a Berry connection one form. Okay, so this is something that you integrate along a line. Okay, so it's a one form. So similarly, one can define the analog of the Berry flux, which is F. And I'm just going to streamline the notation and write this as dA plus A wedge A. So it's sort of the generalization of the curl of A. And so this is the non-abelian Berry curvature. Two form. So this is something that you integrate on a surface. Okay? And so from this, when you're in 4 dimensions, you can define a 4-dimensional version of the Berry flux, sort of. Okay, where what I'm so this is called the second Chern number, which is a integral of a 4-form over the 4-dimensional Brillouin zone. Okay, so F is a 2-form. It's something that you integrate over a surface. Wedge F is a 4-form, something that you integrate over a 4-dimensional volume. Okay, and for the same reason that the first Chern number is quantized, the second Chern number is similarly quantized to an integer. Okay, and so it is possible to have a 4-dimensional band structure whose second Chern number is non-zero. And so this gives a sort of a generalization in 4 dimensions of the quantum Hall effect. And the consequence of that, so remember the consequence of having a non-zero Chern number in 2 dimensions was that you have the unpaired chiral edge states. The consequence of this is that if I look on the boundary state, so the boundary of a 4-dimensional system would be 3 dimensions, so 3 plus 1 dimensional. So you have a 3 plus 1 dimensional chiral Dirac fermion. And this 3 plus 1 dimensional chiral Dirac fermion is the same thing that people now call Weil points. Okay, so it's possible to have in 3 dimensions a Weil point where near this you have H is equal to sigma dot K, and near this and you've used up all of the Pauli matrices. Okay, but in a real 3-dimensional material, a 3-dimensional Weil semimetal, which you're going to be hearing more about probably from Ashvin next week, there's a theorem that says that the Weil points have to come in pairs. Okay, there's a doubling theorem. Okay, sort of like the doubling theorem for 1-dimensional chiral Dirac fermions, and this quantum Hall state evades it in the same way. What's that?
What is I and J?
I and J are labeling different bands. So now I imagine I have a valence band that has, several different bands, and so I have block states associated with each of those bands. So if I have n bands, then in general I have a n by n matrix that I can construct with this. Okay, and so.
Why can't we do such similar construction for lower dimension?
Well, you can do a similar construction in lower dimensions. The problem is that in order to get anything that we haven't already talked about, you need this, and you can't talk about 4 forms in less than 4 dimensions. So certainly So the regular Chern number, the first Chern number I can write as an integral over a 2-dimensional space of trace of F. Okay, and that's the same basically as what I had before.
The trace over the abelian part.
Right, exactly. But in F wedge F, then you get something new.
What's the difference again between Dirac and Weil?
Well, okay. So this is a little bit of a contentious nomenclature issue, and I don't think it's perfect. So I think the term when people use Weil, when people talk about Weil points, they're referring to a point where two bands are touching each other. So it's a twofold degeneracy, which is locally described by a 2x2 matrix, and that's the Weil Hamiltonian in 3 dimensions. Yeah.
So all three polys.
All 3 polys. This is in 3 dimensions. I have kx, ky, and kz, sigma x, sigma y, and sigma z. Yeah. So in 3 dimensions, if I want to talk about a Dirac point, I'd want to have a 4 states be degenerate. For a Dirac or for Weil? Yeah.
If you figure the second term number inherently non-abelian Dirac connections, is it possible to get
No, it's not. I think with a single band, this is going to be stuck being 0. Yeah. No, it does not. That's an interesting question. You can ask yourself, how does this thing behave under time reversal symmetry? Well, under time reversal symmetry, F goes to minus itself, but F wedge F stays the same.
Is there a pumping picture?
A what?
Is there a pumping?
I'm sure there is. Yeah, that's a good homework problem. Yeah.
So when you defined the abelian Berry phase earlier, it was gauge dependent, and the gauge invariant quantity that's useful is computing a Berry phase. You integrate it out loop.
Yeah.
So what's the analog here? What do you get in this?
Yeah. Okay. Really, what it is it's so the abelian Berry phase. Okay. So. So in the abelian case, I can write the integral over some volume of F as the integral over a volume of F is really the curl of A. So that allows me to write that on the boundary of A. Okay, and so this is the Berry phase, and this is I can write that in terms of the flux. So the analog here is I have an integral over, so this is a 2-dimensional, so now I have a 4-dimensional volume, okay? And so in fact, like F, F wedge F is a total derivative. And so it is the total derivative of the Chern-Simons 3 form. Okay, and so one can then write that as an integral on the boundary. So I think this is probably the best generalization of that of this that I can think of. So you could call A, if you wanted to, you could call that the Chern-Simons 1 form. Okay, and then the Chern-Simons 3 form is a little bit more complicated.
My question was more to A, because A is a one form, and I can find a loop in that space on which I can integrate A to get some non-trivial quantity.
Yeah.
So what would that mean? Because Berry phase had a physical interpretation.
Well, no, if you integrate A on a loop, then that's the Berry phase. I mean,
But here it's a matrix. So
no, but it's still going to be. It's only going to pick out the U1 part of the Berry phase. So if I integrate trace of, I have to take the trace. So if I integrate this, then that's going to be the integral, if this is over the boundary, then that's going to be the integral of f over the boundary, trace of f. Okay, I'm still, maybe Nick knows what the question is and what the answer is.
If I take the integral of the third side of the equal, is that some generalization?
I think it is some sort of generalization. I don't know exactly what, I mean, it's an integral over a three-dimensional, it's not a loop integral anymore, it's a three-dimensional integral, but it seems that is the generalization. I'm not sure what, I think you want to attach some physical meaning to it. I'm not sure how to answer that. Yeah.
I just want to point out that you can definitely have non-zero. You take that, but you get it's just like having a theta.
Okay. Okay. All right. Fair enough. Thank you. Good. Okay. Okay. I have 5 minutes left, so let me just say one last thing in 5 minutes, and then one last generalization that I'll do very, very briefly. So I've been talking about sort of uniform band structures that are sort of, a bulk that just has a band structure. What I want to now think about now is band structures that vary in space. And to keep things simple, let's suppose they vary very slowly in space, so that locally I have a band structure, but I can think that band structure is parameterized by where I'm located. Okay, so I want to have a band structure and in particular, I'd like to see if I can characterize topological defects that arise in real space. Okay, and so the simple situation I want to imagine is let's suppose I have a three-dimensional system, but I want to ask whether it's possible to have a line defect. So what I'm going to do is so let's imagine I have a line in my three-dimensional, I'm going to draw a circle around that line. Let me call that S. Okay, and I want to think of how my band structure behaves as a function of where I am on that circle, and imagine that it behaves slowly. So what I can think that I have is I have a Hamiltonian which at every point on this circle I have a band structure which is a function of kx, ky, and kz, but now that varies as a function of s going around this circle. Okay, and so I want to ask the question whether, even though h of k by itself might be topologically trivial, maybe it's a trivial insulator, I want to ask the question whether the family of Hamiltonians h of k and s could be topologically non-trivial. Okay, and in particular, so what we have here now is we have a Hamiltonian which is parameterized by four parameters, kx, ky, kz, and s. And so this then can have a second Chern number. And I will be done very soon. Okay, and when this second Chern number is non-zero, what it tells you is that you have a chiral Dirac fermion edge mode that runs along this topological defect. Okay, and so this is a kind of generalization, if you will, of this bulk boundary correspondence to describe the protected modes that can live along topological defects. Okay? And just as a simple example of this, let me give a trivial example. Let's think about these layered quantum Hall states. I have a three-dimensional system which is a bunch of layered quantum Hall states. And I can imagine the following situation where I have a dislocation in my layer. And so then obviously there's going to be a chiral edge state which lives on this dislocation line. Okay? And so an exercise you can think of doing is drawing a circle here and evaluating this second Chern number on this circle. And what you find it is that you get n, which is basically equal to the reciprocal lattice vector that characterizes my three-dimensional quantum Hall state, dotted into the Burger's vector of the dislocation. So the dislocation involves a translation by a lattice, which is called the Burger's vector. And the dot product of these two is guaranteed to be an integer, and that's in fact what this second Chern number works out to be, and that's obviously what counts the number of chiral modes that you have on this boundary. Okay, so that was the final generalization. So tomorrow, or I guess on Friday, I will finally get to the Z2 topological insulators. I think I'm probably not going to have too much time to talk about topological superconductivity, but that's a topic which I think is going to be covered in depth